Okay, this is the second video for the April 22nd class that I messed up the audio. And I'm re-recording audio on top of the video. First of all, in principle for Laplace transforms, the components resistor, capacitor, and inductor do translate to very similar as in phasors. So resistor is a resistor, inductor is j omega L. Instead here we're going to say in S domain it's SL. And a capacitor goes to 1 over SC because we're talking about impedance in S domain. Recapping, the reason for us use Laplace is that it's a much more powerful tool to solve circuits that makes it simpler than a differential equation and more encompassing than just phasors. So any function, any forcing function can be addressed with Laplace, and here I'm going to show you how to do the Laplace transform for a capacitor. And we know from 285 that's I equals C dV dt. And now doing the Laplace for I of C, it goes to I of S. The capacitor is a constant, so stays at C. If we're doing this in biological systems that have nonlinear components, the capacitor would be the Laplace transform for the capacitor. Here we're just going to do the Laplace transform for the dV dt as S times V of S minus the initial condition, V at 0. Now I'm going to separate the terms, or split capacitor there for the first term. This first one is the steady state component of the capacitor. This is what we used in phasors. If you remember phasors, it was V of j omega equals I of j omega divided by C j omega C. And here's the same thing. Minus C times V at 0. So that part is the initial condition. And this part is a current. So you see that the current is now equal to C times S times V of S minus C times V of 0. That is a current supply. And the minus means that the current supply is going to go against the current on the capacitor. So when we draw this, the sum of two currents will be a capacitor in parallel with a current supply. And the capacitance in times the time in S domain will be 1 over Cs. This is the current through the capacitor there will be split into that current minus C times V0. So the first part of the current is what we already had. And now the arrow is pointing up, making sure you remember this is because of that minus on that initial condition. I apologize that this is not exactly, my hands are not showing things that I'm saying because I just said that, so on the direction of the current. So now I'm going to do source transformation on this circuit, just like we did in the for the inductor. So instead of a current source in parallel with the capacitor, I want now a voltage source, and I'm going to use again Ohm's law, and that's V of S, and it's going to be the voltage across the capacitor itself plus a voltage that is only the initial condition, and that voltage equals Ri. So I'm going to multiply CV0 by 1 over Cs, so the capacitor gets out of that, and the voltage supply is just V of 0 divided by S. The reason for the plus on the top of this voltage supply here is that the arrow, that current, is pointing up. So now I'm multiplying those two and getting V of 0 over S. This voltage supply is just the initial condition of the capacitor. If we have 0, then there's nothing. There is just a short between the bottom of the capacitor and ground, or in the bottom of that circuit. I can also do manipulation here, algebraic manipulation, to put V of S out of that expression on the other side, and then you'll see that we are going to get exactly the same as the source transformation. So if I get the voltage out, I'm going to have the voltage across the capacitor, and the initial condition will be I over S over SC plus V over S, which is the same as what I have there. So in the next video, we're going to solve a circuit using these concepts. These are the only new concepts for this section of the book 16.2. Again, I apologize for the lack of audio. I don't really know what happened to my microphone when I first recorded this.